From ContainerDays Hamburg, this video is proudly presented by Dux IT.
My name is Alexandre Cabral, also known as Alex. You can call me Alex, it's easier. And Mago, it's on the shirt. It means wizard in Portuguese. I work at Stone as a senior software engineer. Stone is a fintech company in Brazil. And today I'll talk to you about memory leaks in Go. There was a presentation earlier today about garbage collection, and probably I'll talk a little bit more about the same stuff. And the name of the speaker was Alexander, so I think it's something Alexander likes to talk about. Yeah, nice. So a little bit more about me. I'm a Golang GDE, Google Developer Expert. The screen, I forgot. I'm Brazilian from Minas Gerais. I'm Genevieve's father, this orange cat on the photo. I'm Tech Hub JF organizer. It's a non-profitable community, tech community in Brazil. You are all welcome there if you go to Brazil to present or watch some of the presentations. This QR code will lead you to my website. At the end of the presentation, it will be shown again, okay? So we'll discuss what are memory leaks today, some examples, and how to monitor them. So let's start with memory leaks itself. Basically, the idea is that a memory leak is a bad memory usage. It happens when you have some kind of object that's being referenced, but actually you don't need it anymore. But since you are referencing it, it still have an address in the memory. And usually has something to do with heap memory. We have two types of memories that we use the most, stack memory and heap memory. The stack memory is faster, but it's limited. And the heap memory is dynamic, so it can grow more than the stack. And it also, the problem is that it's slower. But usually it has to do with the heap because it's where the garbage collector will act. So the problem with memory leaks, where we get these memory leaks, is actually from the garbage collector because it spoiled us. We think that if a language has a garbage collector, we don't have to think about memory, but that's wrong because we have to help the garbage collector to know what it can act over it, okay? So in Golang, it runs after you double the size of memory, the amount of memory that you are using. All right, so as you can see, this kind of peaks that we have on this image, but we can change this kind of configuration. We can tune our garbage collector with this GoGC environment variable. So we can make it run more often or less often, and it will depend on your needs. Because garbage collection actually is a balance between two stuffs, between memory usage and between CPU usage, okay? So whenever you are using the garbage collector you are running, you are losing CPU time that you could be using for other stuff, running logics on your code, okay? And let's go to some cases. The first one is about pointers. So this is a simple code where we have a main function and a process being called. And basically what I'm doing here is creating a variable called value and printing its address on the main function and inside the process one. So as we can see, the address, the memory address is the same, okay? Because we are returning a pointer in this case. But we can return as a value. When we return, we create the same variable here and we return it and print the address. And as we can see, the address is different. It happens because when we return as a value, we actually copy these to another address and then it goes to the main function. So which program uses the heap? Anyone can help me here? Yeah, the pointer one, right? So, but you don't have to believe me. We can see it, what happens in Golang. So we can use these GC flags. The GC is not garbage collection, is Go compiler, okay? M, where we can have more information about what's happening. As we can see, we have some inlining, and we have information about that when we use a pointer, it moved the value to the heap. When we see the value one return, we actually don't have this movement to the heap. This is a kind of memory leak because we don't need this value actually on the heap because we use it just a few moments inside our main function, so it was not needed. And usually, this is a kind of rule that we try to follow. We always try to return and pass parameters as values instead of pointers. And pointers we use only if we actually need them, if we have a good reason for use them, okay? The second case is slices. So in Golang, usually we deal more with slices than arrays itself. So first of all, I will show this is a complementary code that I'm using to print some information about the memory usage, okay? So I'm using this runtime package that I will read some stuff from the memory and converting the heap in use from bytes to megabytes just to be more easy to understand. But basically, slices in Golang, they are actually referencing a underlying array. So they have three properties only: a pointer to the underlying array, a length, and a capacity. So the slice itself doesn't hold any value, okay? Just reference it. So when we do this kind of reslice, this is something very dangerous because actually, in this case, what we are doing is reading a file. So it returns a slice of bytes. But actually, in this situation, I just need half of the file. I don't need the whole file. So I'm doing the reslice from 0 to 5 million. But as you can see, what I'm showing you on the comments, we still have 10 megabytes. Imagine this file has 10 megabytes. The reslice still have 10 megabytes. So we are using only half of the file, but the size is the same. And this happens because of the way that slices works, because they actually point to an underlying array. So this is a kind of memory leak too, a simple one. And as you can see, when we print it, we have 10 megabytes printing on our program. And the correction is pretty simple. Actually, what we have to do is copy this information to another slice. So we use this bytes clone, in this case 4 bytes, and what we are doing is moving this to another address with only half of the values, okay? So this way, we're not using 10 megabytes anymore. We're actually using 15 megabytes. So something wrong happened, right? Because I told you this was a correction. But the problem here is actually that the garbage collector didn't run because our memory didn't double. So the problem is not the code itself, but we can correct it easily using goMemLimit. This variable allows us to actually force the garbage collector to run when we reach a certain amount of memory. So it's not a hard limit. It's not something that will break our program, but it's a kind of tip for the garbage collector to try to let our memory below this level, okay, 10 megabytes. And after running with this goMemLimit, we have 5 megabytes as I promised you. But again, you have to think about your situation, what's best for you, because this way we are using less memory, but we did one more allocation, right? Because we cloned it to another memory address. So you have to think what's best for your situation. And as you can see, memory leaks, they are pretty easy, pretty simple. And usually when you do something with your code that leads to a memory leak, usually you feel like an idiot because it's pretty simple, but it can happen. And with the usage of AI, you have to be you have to have more attention than ever because AI usually depends on others' code, and many of this code have memory leaks. So always watch out for memory leaks, especially if you don't know Golang that much. You have relying on AI-generated code is a little bit dangerous, okay? So we have to always keep looking into our code and understanding the language. This is pretty important. And there are more examples. I don't have time here, but like lack of eviction policy, we have maps, slices, and usually you just insert stuff. You don't think about removing bad usage of defer because there are situations like the defer, it will act at the end of the function, not an iteration. So if you use a defer inside a for loop, maybe that's a problem. And open channels, because usually we use channels to synchronize goroutines, right? But if you forget to actually drain your channel and close it, it's a memory leak because it will keep using that memory space. But let's go to how to identify memory leaks, because I'm talking to you about these memory leaks. Now you go back to your companies, you won't commit those problems, you won't make it happen again, you look into your code and that's all great. But the problem is there are lots of code inside your company already and other people writing it, maybe this person is not here today. So there are ways for you to identify it in a better way than just looking into lines of code, okay? And there are three main ways to do it: benchmarks, metrics, and profiling. With benchmarks, it's a simple test in Golang that we can do. It runs a couple times, and we have information about not only, usually we think about time complexity, but we have space complexity too if we use bench mem for having memory information. And as you can see, we have this nanoseconds per operation for time, and we have bytes per operation and allocations per operation too. So if you know something is wrong with your code and you know a little bit where the problem should be, this is good. So it's something more local, okay, inside your code. You have metrics. So like I told you before, using the package, the runtime package, you can read things from memory and then printing it using this kind of stuff, but printing is not the best one. The best way to deal with metrics, actually the idea is to use it continuously, to send this information for, this is Datadog, so you can send to any observability tool that you want, and have information more about the holistic about the application, so the whole application itself, a broad view. So in this case, is a little bit different from what we've seen with benchmarks, right? And profiling actually is like the best of the two worlds, because you have information about what's happening inside your code, like function by function, and also information about the whole program, because it will show you all the paths that's happening in your code. So it's actually a resources snapshot. It talks about the complexity in your code, time and space, and it helps you with optimizations for your code, like in memory, time. And for Golang, we use pprof. This is a Google tool that we can generate protobuf files that contains this kind of information about profiling and allows us analysis of this data, okay? And to generate these profiles, we can run profiles with tests, runtimes, like the runtime package that we saw before, and endpoint. Usually we use the endpoint because it's easier to deal with. And this is the example, and it's pretty simple. What you have to do is just importing this package, net HTTP pprof, with an underline. This is telling Golang that you actually need this package, even though we are not mentioning it anywhere in our code. We are not using pprof. And you are telling Golang that don't vanish with this, I need it. And how does it work? It's a kind of magic at the end, because it has this init function. And in Golang, the init function will be called automatically. Any package that has this init function will make it run automatically, okay? And it just creates some handle functions, so the handlers for us, for our API. So at the end, we have some endpoints for running the profiles, okay? So heap, goroutine, profile, that's the CPU, mutexes, and other stuff. And we can download this profile, run this profile, and download it to a file using curl, for example, outputting it, and we can pass some options when we run the profiling. So like forcing the garbage collector to run, running for some time that we want. And we can analyze these profiles with the UI or the CLI. We can choose, but usually I say it's better to use the UI. It's easier to understand. The CLI does the same, but yeah, it's your choice. With the UI to run it, Golang is nice because it's like an ecosystem. You have all the tools that you want inside of it. Usually you don't have to install something from outside. The standard library is great, and we have the tool right here using goto pprof. So you can open the file, or you can hit the endpoint with the goto pprof too. And the used profile will be that example I showed you about the reslice, okay? This will be the information inside our profiling here. And this is the main page, the main screen that we have when we open the pprof, okay? And as you can see, we have lots of options, lots of views to choose. You have to choose what suits best for you. This is the main one, the graph, where you have all the processes that are running inside your code while you were running the profiling. So the red one usually means that's something bad, and yeah, this is the bad one. This is the one that's consuming most memory in your code. So you can focus on it, and usually it will be the code you are actually running, your functions that you are using for tests or this kind of stuff. So if we zoom it, you can see all the stack trace that's happening in your code. So you have each function and which function what it was called from it, and you have information about memory. So in the lines, you have a number like 10,000, 248 kilobytes. That would mean that everything that's below this line, summing, adding everything will sum to 10,000, okay? And inside the boxes, you have the contribution for each function. So there are lots of functions that will be zero of something, because these functions itself, they don't contribute with memory allocation. Actually, they are just calling another function that's contributing. But the OS read file is a standard library function. It doesn't matter to me. What matters to me is what's happening up in my graph. That's the function that I created for my tests, the read file details leak, okay? And this is another view. This is great because you have side by side your code and the memory information of what's happening on each line, okay? And this is good because it's easier for you to understand for developers. You can find actually you were guilty and where is the problem that you inserted. And you have the best view, that's the diff. And this is great because actually you can compare two different profiles. So imagine a situation that you have an API, you created a version, and you want to do like 1.0, and you want to create a new version, 2.0. So you generate one profile with the first one, then you upgrade, do some stuff, optimizations, and then you create the second one. You can compare both and understand if you did something wrong or if you actually optimized something in your code. So it helps you doing this, understanding what happened, and this is important. You must have data to understand. Maybe you think you optimized something, but at the end you don't have data. You are just guessing. So with profiling, with benchmarks, you can have this information. You can back your decisions with data. And in this case, we have a new color here. This is a new Power Ranger unlocked, the green one. And this is good. Usually it's good, green, and it is, because actually what we are doing is the second one, where I put the bytes.clone, okay? So, like I said, we removed 10 megabytes that were allocated. So as you can see, it's green. At the end, we have minus 10 megabytes, but we have a new red branch here. And this is because, like I told you, we did a new allocation that weren't there before, okay? So bytes clone is a new function. It's consuming more, 5 megabytes, but at the end, when we sum it, it was good because we removed 5 megabytes, okay? But you might be thinking that's too much effort because we have to put these endpoints and then hit them and then open with pprof manually and understand it. It's a little bit too much effort, and doing all the time is a little bit boring, and I wouldn't tell you to do it this way. Actually, what's better, like we did with metrics, like I told you, we do it with logs, metrics, traces. We can do it continuously. So many of the observability tools in the market, they already support profiling continuously. They receive this information, okay? Even OpenTelemetry, it's working now. They have a new way, a new pattern for profiling they are working with. It's not ready yet for production. I think it's in discussion yet, something like this. There's someone that knows a lot about OpenTelemetry there if you want to talk to him. But it will be there with OpenTelemetry. And the great thing is actually that you don't have just the profiling continuously. You can cross information with metrics, with other stuff about your application. And I'll show you an example of how easy it is with Pyroscope, because it's a free open source tool that you can put it running inside your infra. And with Golang, it's pretty simple. You just have to import this package, Pyroscope Go, and you start it. Then you pass the name of the application, the address of Pyroscope, and the tags. Tags will help you actually to filter what you want inside the Pyroscope dashboards, so you can compare versions easily. And also, you can choose what kind of profile that you want to collect. Another thing that I was thinking about, because other presentations people asked me, if there's an overhead using profiling. And yeah, there is an overhead for CPU, but it's usually pretty low, okay? Around like 1%. At the beginning when we had profiling at the beginning of Golang, it was a little bit bigger, like around 10%. But the Go team do a great work, and they are even reducing this kind of overhead, so it's production safe, okay, to do it continuously. Of course, you can choose from time to time that you want to collect more or less profiling stuff, data. So it's your option. You can test it before running in production. And you have all these graphs with information about like CPU process, memory, and everything. And this kind of view, that's the same that I showed you, the same idea that I showed you with the pprof UI, but in this case inside Pyroscope, where we have the difference between two versions. So you can compare filtering by tags, like the version of the application, and also in time. You can select a time window to compare. And you will have information about like that green color that we like, with information about functions that we removed, and also which ones were optimized with less memory usage, okay? And let's talk about a special case that's a goroutine leak. And goroutine leaks, they are actually memory leaks, because goroutines, even though they are lightweight for memory, they still occupy some memory, okay? So basically, goroutine leaks happen when we have a goroutine that's locked. It can't die because something blocked it from dying, from continuing. And usually what happens is actually that you do something wrong with channels, because channels are used to synchronize goroutines, right? And the main cause of goroutine leaks is early returns, one of the main, okay? But there are some other options. So in this case, what I'm doing here is creating a error channel, and I have a goroutine function that I will process something and consume, and I will produce to my error channel the error that happened in my process. After, I have a request, and if something goes wrong, I return. And then I have the consumer. But the problem here is that I have an unbuffered channel. So unbuffered channels must have an active producer and consumer at the same time. If you don't have an active consumer or producer, one of the goroutines will get locked, okay? Will get blocked here. And this is not a compile error, so you can run this code, and so it's a runtime stuff that can happen. Compiler can help you, okay? So in this case, we can have an early return in this request if something goes wrong. So we lose our consumer. So the goroutine up will be blocked, okay? So this is a goroutine leak. The correction is pretty simple. We just have to transform this unbuffered channel into a buffer channel. So what happens is that we have a buffer to hold some value until you have a consumer for it, or even though you don't have a consumer. So it will be possible to produce this message even though you won't use it, okay? So this is a correction for the goroutine leakage, okay? And let's talk about a quick story that happened on my company. I worked on an endpoint for a e-commerce that we have for payment machines. And one of these endpoints was for validating vouchers, okay, discount codes. But the problem, I was working a similar code to this one I showed you, because we had different different sources of vouchers that we could use. Like we have different brands inside our company, okay? So And I had this problem there with an early return. That's the same idea. But it was very difficult to understand what was happening. And this is because we have two different types of memory leaks that can happen. You have the big ones, like this one, on the left, my left, your right. And we have the small ones. The small ones, they are the worst because it's too hard to identify them. When you look into the graphs, you see just a little difference on your graphs, like little ascending curves. So it's really hard to understand that a memory leak is happening. If it's big, you just look at the graph and you understand what's happening, okay? You look into the dashboard and you see, you have alerts, they will show information about it. But if you have a small leak, it will not show you. And the problem is not that small leaks are a problem, but there are situations these small leaks can get huge. And in our case, it's like I said, we had a voucher endpoint, but usually we didn't have that much vouchers. But there was a situation that we would have a huge amount of vouchers being used, and that was Black Friday, okay? But it hadn't happened before because it was the first time we had just built the e-commerce. So what we can do to understand and try to see what can happen in our code in every situation is anticipate this kind of impact. We can simulate the situations using load tests. And this helps us to understand the reality of the memory leak that we are dealing with. And this is an example using K6. K6 is a Grafana tool that we can use for load tests, okay? And this was very small, actually. 10 views for 1 minute and 30 seconds that we had. And as we can see here, our goroutines went from 50, that was the default state that we were expecting, until 300, and it wasn't descending. It stayed there, okay? And this is after the correction. So after I transformed the goroutine, the channel itself, from an unbuffered channel into a buffer channel, we can see that we went from 50 to 75 goroutines max, and it was descending at the end, going to our expected number of goroutines. And for goroutines, we can use another tool that makes our lives easier. That's the goleak from Uber. I advise you to use it because it will show you the exact location that you have a problem with goleaks, okay? And the takeaways of the presentation are basically observe and understand your code. So it's important for you to understand the language you are working with, because each language has its own traps for memory leaks. Okay, Golang, for example, has goroutine leaks. That's a little bit different from other languages, and it's important to observe it and not only print stuff and try to do like eventually. You have to do it all the time. You have to send this kind of information continuously. So metrics, logs, profiling, everything that you can to help you identify these kind of problems. So, and you also, it will help you anticipate your failures. The failures of the application, because you have this kind of information previously. You won't have to wait until the user call the support to say that something's wrong. You don't have to wait until your system stay down for 1 hour and you're losing a fintech like $1 million in an hour. So this is a huge problem. And this kind of thing helps you have data to back your decisions. So you're having data that something's wrong, you can really understand if what you did was good for the application, if it really optimized it, it's not guessing, it's data, okay? And it helps you talk to the product managers and make them understand that you need to spend time doing this kind of stuff during your sprints, because it will help you to not let your system down at the end for a long time and the user face the problems. And like I said in the beginning of the presentation, it's managing your resources better. And the main resource that we want to manage better is your time, because you don't want to get on a Saturday evening watching your football team game and receiving a call, an alert to do something. You have to prevent and working during working time on the weekdays, working days normally, and just prevent it before it becomes a real problem, okay? So that's it. Thank you so much. This is my website, my QR code.
In your reslice example, isn't the 10M memory of the copy still correctly freed once no longer accessible? Aren't you just using more memory than expected?
In the 10 memory, copy is still correctly freed. Once it's no longer accessible. You mean like when the first one when I didn't clone, maybe? Yeah?
I think so.
Okay, so in that case, actually, if we keep our code using that reslice, it won't be freed. But if you don't use it anymore, but the idea there of that example is to use that reslice, okay? The idea is that we be using or the bytes clone or the reslice result. So we still be using what we referenced, okay? So that's why it won't be freed. But if the code was just that, yeah, you were right. But they were pretty simple examples just to show you the situations. But usually you have more code than this, okay?
Awesome. So Jonathan, if you meant something completely different,
yeah,
you're still around, Alex, right?
Yeah,
so
you can talk to me during coffee break and that's it.
Awesome. Does pprof heap leak potential secrets in memory like it happened, e.g. with Spring Boot actuators heap dump?
Okay, so I don't have information about the Spring Boot actuators, but I don't know. I don't have this information if pprof have something that's dangerous to your code. At least I haven't seen anyone from the Go team talking about it, so yeah, I would assume no, but I don't know.
Okay. Is it a good idea to invoke the garbage collector manually?
Yeah, it's not about like if it's a good idea or not. It depends on the situation. Maybe you have a code, because we have different kinds of codes. You have APIs, you have workers, you have scripts that you can run with Golang. Maybe in your situation, it can be a good stuff to do, to call the garbage collector. So it's not something like wrong, okay? You have to understand in your situation. So.
Thank you. So next question is about any effective alerting that can be put in place to notify and catch early leaks.
Yeah, so usually you can create some alerts for the memory, like we saw for metrics, okay? So heap news, so if you see a huge peak happening, so you understand like what's the default that you are expecting. If you see a huge jump, then you can set an alert, or you can see information like when you have a new deploy and you see a huge drop. This usually indicates that you have a memory leak because your code is not releasing, but when you do a new release, you have a new instance up, so this new instance will be freed from the memory leak in this moment. So usually this kind of huge steps that you have, up or down, you can put some kind of alert for it, for metrics, okay?
Wonderful. Thank you so much.
Thank you.
So then, final round of applause for Alex.
From ContainerDays Hamburg, this video is proudly presented by DAX IT.